An instrument approach is a series of predetermined maneuvers for the orderly transfer of an aircraft under instrument flight conditions from the beginning of the initial approach to a landing or to a point from which a landing can be made visually. When your knowledge of radio navigation and route charts and ATC procedures has brought you within striking distance of your destination airport, it is the instrument approach procedure that will bring you down safely to an altitude below the cloud bases from which a normal landing can be made. An instrument approach requires flying specified courses and altitudes for particular lengths of time, radio setup, and ATC reporting. To ensure that all tasks are performed at the right time and in the right order of priority, a reliable technique is required. The 6 T's is a time-tested technique and should be used without fail every time you make a turn and every time you cross a fix. The 6 T's: turn to the desired heading, time, start timing the segment if applicable, twist, turn the OBS knob to the desired course, throttle, adjust power, talk, report your position if necessary, and track, start tracking your desired course. Learning to adhere to this rule may be the single most important lesson for the instrument pilot in training. Just as the GUMPS check ensures that the landing checklist is properly completed, the 6 T's guard against forgetting any important job during the approach. There are 2 broad categories of instrument approaches: precision and non-precision. The difference, while very important, is only in the conduct of the final approach to the airport, where a precision approach provides electronic descent guidance and a non-precision approach does not. Up to the final approach fix, the following discussions of segments, fixes, altitudes, and procedure turns apply equally to precision and non-precision approaches. Cleared for approach. This clearance authorizes you to fly the procedure on the approach plate and to descend to the published altitudes. You may not descend during an approach until you have received approach clearance and are on a published route. The published route may be any approach segment, transition, or airway. If an airway, you may descend to the MEA, but be sure it is higher than the transition or initial approach altitude. Otherwise, you will find yourself climbing later on. When flying direct to an approach fix, you may not descend even if cleared for approach until you are on a published route. This diagram shows the segments of a typical approach. The names and arrangements of the segments do not depend on the type of approach we assume it to be. An approach may have as many as 4 segments and 1 or more published transitions from the en route environment. Each segment and transition has a clearly defined course, a beginning and an end, and a published minimum altitude. The pilot has certain tasks to accomplish during each segment of the approach, and understanding the various segments of a particular approach is important in planning how the approach is to be flown. Transition, the general term that describes the change from one phase of flight or flight condition to another. In other words, transition from en route flight to the approach, or transition from instrument flight to visual flight. Initial approach, the segment between the initial approach fix and the intermediate fix, or the point where the aircraft is established on the intermediate course or final course. Intermediate approach, the segment between the intermediate fix or point and the final approach fix. Final approach, the segment between the final approach fix or point, glide slope intercept for precision approaches, and the runway, airport, or missed approach point. Missed approach, the segment between the missed approach point or point of arrival at decision height and the missed approach fix at the prescribed altitude. This plan view shows a transition from one en route fix to the Pensacola NDB. Transitions are also called feeder routes. Assuming the pilot has received approach clearance, the pilot may descend to the altitude published on the plan view for the transition he is on. The initial approach fix marked IAF on the plan view is the Pickens NDB and is the point where the approach begins. The initial segment begins at the IAF and is the procedure turn outbound segment of the approach. It includes the entire procedure turn and ends when the airport is established inbound to the fix. During this segment, the pilot should slow the airplane to approach speed and descend to the published altitude of 1,500 feet. This particular approach has an intermediate fix, Pierre intersection. The intermediate segment begins at Pierre intersection when the aircraft has turned inbound on the 346-degree bearing and ends at the NDB. Minimum sector altitudes, MSA, are not to be used during an approach. They are for emergencies only. Here, we see a 25 nautical mile circle at the top right corner of the approach plate. The notation MSA, PKZ, NDB indicates the center of the circle. It is during the procedure turn inbound segment of the approach that it's a busy time for the pilot. Here, the final landing checklist should be completed and the missed approach instructions memorized. Since the altitude specified for this segment is lower than that for the initial segment, the pilot should descend to 700 feet. The final approach fix, FAF, is the Pickens NDB and is identified by the Maltese cross on the profile view. It marks the beginning of the final letdown to the airport. When not in radar contact, the final approach fix inbound must be reported to ATC. On this approach, the final approach fix is the NDB, and the intermediate fix is located at Pierre intersection. The final approach segment is the course from the final approach fix to the missed approach point. During this segment, the final descent to minimums is made. Since this is a non-precision approach, in other words, there is no descent guidance, the pilot simply descends to the minimum descent altitude, MDA, of 500 feet, and levels off, carefully tracking the 346-degree bearing from the NDB until the missed approach point, MAP, is reached. On this approach, the missed approach point is 1.5 miles from the NDB, and it is usually identified by timing the final approach segment. In some cases, the final approach segment is divided into parts with different altitudes separated by step-down fixes. A step-down fix may be defined by a crossing radial, a DME fix, or a fan marker. Assuming the runway is not seen, the missed approach segment begins at the missed approach point. It is crucial to immediately initiate a safe climb away from the terrain. The pilot should not have to refer to the approach plate for missed approach instructions now, but should have memorized them before beginning the final approach. While a missed approach requires an ATC report, the first priority is to climb away from the ground and begin the missed approach procedure. The radio call can safely wait a moment or two. The missed approach segment for ILS runway 4 right at Chicago O'Hare consists of climbing straight ahead to 1,200 feet, then making a climbing right turn to 4,000 feet via outbound VOR radial 089 degrees to Laird intersection and hold. The hold at Laird intersection is the published hold. This is shown in the plan view and missed approach section of the approach plate. If the runway is seen, a landing can be made. A straight-in landing is a landing on the runway referred to in the approach name. Landing on other than runway 4 right constitutes a circle to land maneuver and requires the use of circling minimums, even if no actual circling is done to line up with the desired runway. If an approach name does not specify any runway, as in the Rochelle, Illinois VOR-A approach, no straight-in minimums are shown. At a field with no control zone, circling presents an additional problem. Below 700 feet AGL, you are in uncontrolled airspace where VFR minimums are 1 mile and clear of clouds. There just might be somebody in the pattern practicing touch and goes, and you are both legal. Broadcasting your position and intentions on Unicom is your only defense against this danger. The large numbers in the minimums box give minimum descent altitudes, MDA, above sea level, MSL. In the straight-in landing section, the parenthetical number is the height above touchdown, or HAT. Adding this number to the touchdown zone elevation, TDZE, shown in the profile, gives the MDA. 564 plus 1076 equals 1640. The touchdown zone elevation is the highest point in the first 3,000 feet of the runway. The parenthetical numbers in the circle to land section are height above airport, HAA. This, plus the airport elevation, the highest point on any runway, also equals the MDA. 564 plus 1076 equals 1640. The highest obstruction on a Jeppson plate is shown by the curving black arrow. An approach may not have a full complement of fixes, segments, and transitions. This approach shows an approach with no intermediate or final fix and no intermediate segment. On this approach, descent to the MDA is initiated at the completion of the procedure turn. The procedure turn. A procedure turn is a maneuver used to reverse direction and establish the airplane inbound on the intermediate approach segment or final approach course. If a conventional turn is shown on the approach plate, as in the illustration, the turn must be accomplished within the specified distance, usually 10 nautical miles, at or above the specified minimum altitude and on the specified side of the course. Distance and altitude information are obtained from the profile view of the approach plate. The outbound distance flown before the turn is started is left to the pilot's discretion, as long as the turn is completed within the required distance from the fix. Usually 2 minutes outbound allows sufficient time to become established inbound and descend as necessary before reaching the final approach fix. In extremely windy or turbulent conditions, the pilot may choose to lengthen this time. The headings flown in a procedure turn are not mandatory and may be altered by the pilot to compensate for wind conditions or personal preference. Some alternate procedure turn patterns are shown here. Notice that there is no choice as to which side of the course the turn is made on. Some approach procedures prescribe a teardrop maneuver, as is shown here. This is in lieu of a procedure turn. The teardrop is mandatory and must be flown as shown. Here we see a VOR approach with a holding pattern in lieu of a procedure turn. The holding pattern maneuver is also mandatory, and the pilot is expected to make an appropriate entry to the depicted pattern. The minimum required number of turns in the hold is 1, including the entry. That is, cross the fix twice, once outbound and once inbound. The length of the holding pattern leg is usually 1 minute and is shown on the profile view. If you need more time to get established inbound at the proper altitude, advise ATC that you wish to make another circuit in the hold. Do not extend the length of the holding pattern legs. Notice that the hold at the Peoria VOR is at the initial approach fix and constitutes the initial approach segment. At the completion of the hold, you are back at the VOR, which is now the intermediate approach fix, although it is never marked as such. The intermediate segment then takes you to the final approach fix, Bruin intersection, defined by 9 DME miles or a radar fix on the 240-degree radial of the Peoria VOR. Notice that DME or radar is required for the Canton-Ingersoll VOR-A approach. In addition to NDB, VOR, and VOR DME approaches, there are several less common types of non-precision approach. A localizer approach provides very accurate course guidance to the threshold of a runway. With a localizer frequency in the navigation receiver, the CDI is approximately 4 times as sensitive as when tracking a VOR course. The width of a localizer course is 3 to 6 degrees, approximately 700 feet at the runway threshold. The CDI responds to the localizer course regardless of the OBS setting. The OBS has no function except possibly to remind the pilot of the course. Since a localizer is a component of the ILS, every ILS approach plate has LOC, or glide slope out, that's GS out, minimums published in the minimums box. In the event that a glide slope receiver fails or the glide slope is out of service, the pilot can make a localizer approach by referring to the time and ground speed box and timing from the final approach fix. A localizer type directional aid, or LDA, is a localizer that is not aligned with a runway. It provides the same accuracy but does not bring the aircraft down the extended center line of the runway as does a localizer. There may be straight-in minimums authorized if the LDA is aligned within 30 degrees of the runway. Airport Surveillance Radar, ASR, approaches are available at some terminals. The controller uses a special large-scale radar screen to accurately vector the airplane to the threshold of the runway. The pilot is continuously informed of his distance from the runway and his position with relation to the course center line. He will be informed when to descend to the MDA. If on the final of an ASR approach the pilot receives no communications for 15 seconds, the rules require a missed approach. At fields where there are published ASR approaches, Jeppesen publishes separate plates for ASR approaches, controllers are required to maintain ASR accuracy, so they are often willing to provide practice for you, the pilot, when their workload is not too heavy. A precision approach provides descent as well as course guidance. It requires that the pilot develop the skill to control his glide path according to needle indications in the cockpit or verbal instructions from a controller on the ground. The missed approach point on a precision approach occurs when the airplane on the glide slope reaches the decision height. At this altitude, the pilot must either make visual contact with the runway or runway environment or execute a missed approach. There is no leveling off at decision height. Either continue visually to a landing or immediately start the missed approach. The outer marker is roughly 5 miles from the runway, approximately where an aircraft at the intermediate approach altitude will intercept the glide slope. The middle marker is approximately 1/2 mile from the threshold, about where an airplane on the glide slope reaches decision height. There may be a low-power NDB known as a compass locator at the outer or middle marker. These are then called locator outer markers, LOMs, or locator middle markers, LMMs. In addition to the 4 elements, outer marker, middle marker, localizer, and glide slope, an approach lighting system, or ALS, is usually associated with an ILS. These systems offer a large array of brilliant lighting as far as 1/2 mile from the runway. They can be seen by the pilot in all but the worst of weather. The decision height on the typical ILS is 200 feet above the touchdown zone. A Category 2 ILS offers a decision height of 150 or 100 feet above the touchdown zone, but is usable only by specially certified aircraft and crew. Before you reach the initial fix of an ILS, there may be as many as 5 radios to set up. The ILS frequency itself must be tuned in to the number 1 nav radio and identified. If there is an outer compass locator, it should be tuned and identified on the ADF. The marker beacons should be tested and the audio switch and volume control checked in the right position. If you are working approach control, the tower frequency should be entered in your other comm radio to avoid having to switch frequencies at a crucial moment of the approach. Lastly, the second nav radio may need to be tuned to the missed approach fix or to a step-down fix. On the ILS, there is some heading which will exactly compensate for wind and keep the airplane on course. It is called the reference heading, and your first job is to determine, by bracketing, exactly what this heading is. It may equal the course shown on the approach plate, or, owing to wind or DG precession, it may be something different. As the aircraft starts to intercept the localizer, the CDI will move from full-scale deflection towards the center. As soon as the needle moves, begin turning the airplane toward the final course, assuming approach clearance has been received. When the CDI stops moving, stop turning. The DG now shows the first approximation to the reference heading. If the needle moves slightly, turn 5 degrees toward the movement. Continue bracketing with smaller turns until it stops completely. As long as the CDI is stationary, you are a constant number of degrees off course. Since the localizer narrows toward the runway, you are actually getting closer to its center line. The important step at this point is to note the DG and mentally record the reference heading. Once the reference heading is known, it is a simple matter to center the needle. Turn 5 degrees toward the middle, 10 degrees if deflection is more than half scale, but this is the maximum turn on an ILS once the localizer is intercepted. And then as the needle centers, turn back to the reference heading. It is crucial while flying the ILS that all turns be made with reference to the DG. As you descend on the glide slope, the wind may shift and the reference heading may change. This will be apparent as a correction towards the needle stops, but it does not bring it in. The new heading is now the reference heading, and further correction should be made in relation to it. On an ILS, the final descent is begun when the glide slope is intercepted, not at the outer marker. Glide slope interception does not usually coincide exactly with marker passage. As the glide slope needle centers, establish your approach descent configuration. On a day with a strong headwind, your reduced ground speed will require a smaller than normal rate of descent, a higher pitch attitude, and therefore a higher than normal power setting to maintain the desired indicated airspeed. Once the power has been set, glide path corrections are made with small pitch changes. There is a particular descent rate which will keep the aircraft on the glide slope with the existing wind and power conditions. This is the reference descent rate. It must be determined by bracketing on the VSI in a manner similar to bracketing the reference heading on the DG. Pitch changes are made with reference to the artificial horizon and evaluated on the VSI. If at some point during the approach a half-scale deflection or worse occurs on the glide slope indicator, the power setting should be changed 1 inch of manifold pressure, or 100 RPMs as the case may be. Otherwise, correcting such a large excursion with pitch alone would result in too much change in airspeed. The altimeter must be kept in the instrument scan during an ILS approach, and it may be helpful to periodically call out the number of feet remaining to decision height. The purpose of visual and contact approaches is to save time. Instead of executing a full instrument procedure or flying a circuitous series of vectors, the pilot simply flies to the airport and enters the pattern. The time saved is usually 10 or 15 minutes. A visual approach clearance may be issued by the controller or requested by the pilot when the aircraft is in VFR conditions and can remain so throughout the descent and landing. The pilot must maintain VFR and safe separation from any aircraft he's instructed to follow. Aircraft may be vectored for a visual approach when the ceiling is 500 feet above the controller's minimum vectoring altitude. A pilot may refuse a visual approach if he prefers to conduct an instrument approach for practice or for any other reason. A contact approach may be conducted even when the weather is less than VFR. It requires only 1 mile and clear of clouds and must be requested by the pilot. During a contact approach, ATC will provide IFR separation, but the pilot is responsible for obstacle clearance. If he cannot maintain cloud clearance or visibility falls before 1 mile, the pilot must immediately advise ATC and alternate instructions will be issued. In another VTA videotape, emergency operation will be included, such as communication failure, electrical failure, vacuum failure, engine failure, and weather emergencies such as thunderstorms and icing.